Hi everyone. This video will cover the first part of the Chapter 6 portion of the exam review. This chapter included material on roots, powers, and logarithms, so kind of a lot packed into this chapter. And this whole first page is dealing with logs, so I thought before we would get started, we should take a minute and just review some of the properties of logs. Um, so just to remind you, logs have sort of their own set of rules when you're working to manipulate them algebraically. So when you're trying to combine them or take them back apart, they don't follow normal math rules. And the reason for that is they're really exponents in disguise. So if you think about when we work with exponents, they kind of follow their own rules too for the way you combine them or manipulate them. So for example, if I'm taking two logs and adding them together, two separate logs. That's the same thing as taking a single log of the two numbers here being multiplied together. So addition of logs is equivalent to multiplying the two terms together. Similarly, subtracting two logs is equivalent to taking a log of the quotient, so that's division, A divided by B. And then the third one you should know is that if I try to take the log of something with an exponent on it, just because these are all exponents already, that's really equivalent to taking that exponent and multiplying by the log of A. So let me just back up a second here. The reason this works the way it does, this log A plus log B is equivalent to log of AB, is because if you were to try to do, for example, x to the third times x to the fourth, if you're doing multiplication, the exponents would actually end up getting added together, and you would end up with x to the seventh. You would add the two powers together. And logs are really exponents. So that's the idea here. Same thing if I were to do division. If I was to turn this into division, you would tell me that I'm supposed to subtract those exponents, and that's what's happening here. So division leads to subtraction. Multiplication leads to addition, just like that works with exponents. And then with powers, if you were to do something like x to the third to the fourth power, raising a power to a power, we combine those by multiplying. And that's exactly what's happening here is I take this and I multiply by the other exponent. So understanding that anytime you see a log, it's really talking about an exponent kind of makes these rules make a little more sense. You're going to have to be able to work with these rules in both directions. So sometimes I'm going to give you something separated and you have to put it back together. Sometimes I'm going to give you something like this, and for whatever reason, you're going to have to take it back apart. So you'll want to know these properties kind of forwards and backwards here. So for example, in this first one, rewrite as a single logarithm. That's me giving you something separated, so something like what we have over here on the left, and asking you to smush it back together. So the very first thing I would do to get things put back together is this 2/3 really is an exponent, right? That 2/3 really belongs over here as an exponent on the B. And then because this is subtraction, I'm going to combine the B and the C with division because I see subtraction between the two logs. So the way I would write this would be log base 7 of one big expression here, and this is going to be B to the 2/3 power divided by C. Notice it's not a log divided by another log because the whole idea here is to write it under one log umbrella. Okay, so that would just be my answer there for number 1. So number 2 is going to be similar. The goal is to write this as log, oops, gotta grab a different pen here. Sorry guys. Log base 7 of something. When I smush these back together, I know this 3 needs to go up here as an exponent, so I'm going to get rid of that. And then I'm going to multiply the B and the C and divide by the 5. So I'm going to go B times C to the third divided by 5. And again, when it's a single logarithm, your goal is to have just log of one big thing. Okay, so now we're going to get into solving with logs. And so I'm going to show you how to do that with this problem, knowing that we're going to use kind of a similar method all the way down the page here. So when I say log base 2 of 12, the question I'm really asking is what exponent do I need to make a 2 into a 12? Okay. Now, if this was something more obvious, if this was like a 16 or a 32 or some perfect power of 2, you may be able to just come up with that exponent off the top of your head. But when you don't know what that exponent is, and you've got an x up in the exponent, you're going to hear me say this a lot. Anytime the x is in the exponent, the way we're bringing it down is using this log property, that if I take the log of something with an exponent, I'm allowed to bring that exponent down in front. So I'm going to take a common log on both sides here. And that's going to allow me to take this x and move it down in front. So now my equation reads like this. X times log 2 equals log 12. And it was the log that allows me to bring that x down. Sometimes I see people like dropping that exponent down in front before they put the logs on there. That doesn't make any sense. It's the logarithm that allows you to bring the x down. And then I want that x by itself, so I'm going to divide by log 2. And let's see. So now I'm just going to do log 12 divided by log 2. And there's my answer. It says round to the nearest hundredth, so I'm going to go 3.58. Okay, so with this next one, there's actually two different ways you could go about this one. This 5 really belongs up here as an exponent on that 42. That'd be 42 to the 5th power, and then I would kind of work through it the same way I did up here. I'm looking at this and just thinking that 42 to the 5th power is going to be kind of gigantic. So what I think I'm going to do instead, and it's not wrong if you did it the other way, but I'm going to just worry about this right now. I'm just going to see if I can come up with this answer. And again, this thing here is asking the question, 7 to what power makes 42? I'm going to do that the same way I did up here. Now, once you've done a few of these, you may be able to kind of jump some steps here. You might not have to write this out every single time. Okay, you know I'm still going to, but. So we end up with x times log 7 equals log 42. Then I could divide by log 7. So what I mean by that when I say that some of you might be able to jump steps is some of you are going to get to the point where you can just look at this and go, oh, I need to do log 42 divided by log 7. That's always going to work for you. That was actually a property we learned called the change of base property. So if you're comfortable with that, you are more than welcome to do that. But this process is something you can always fall back on if you forget. So log 42 divided by log 7 works out to be 1.92. But remember that that is just this log part. The question wanted to know what's 5 times that number. So I'm going to go 5 times 1.92. And my answer here would be 9.60 as a final. You could have done this a different way. So you could have moved that 5 up here as a power on the 42, figured out what 42 to the 5th power is, so something gigantic. 42 to the power of 5, okay, is that giant number. And then you would have really ended up doing this, log of the giant number divided by log 7. So watch here, log of that big number divided by log 7. And notice you still end up in the same place. Okay, so you could have put that up there as an exponent to begin with and then work the rest of the way through your problem. What you wouldn't want to do is take this answer and raise it to a power of 5. Either you put the power of 5 on the 42 before you begin everything else, or you save it for the end. But you can't kind of mix steps there. Okay, so with number 5, you'll notice kind of starts me in the same place that I started here. I'm just taking a log and a log, so that I have x times log 3 equals log 0.27. To save myself some time, I'm not going to write out all those in-between steps. I just know that I need to do this log divided by that log to get x by itself. So let's try that. Log 0.27 divided by log 3. And I end up with negative 1.19. Makes sense to me that that's negative because I'm taking a 3 and using a power to turn it into some smaller number. Okay, same thing here. Log. This is the technique I'm using anytime x is in the exponent. So x times log 11 equals log 0.77. Divide this log by this log to get x by itself. So log 0.77. This is another one that I'm expecting to come out negative. Divided by log 11. And x equals negative we'll go 1 because it said nearest hundredth. Okay, on number 7, the only thing that switches up just a little bit is this 5 here. What I want you to be careful of is we can't combine the 5 and the 2. That would be breaking order of operations because technically this power needs to apply to the 2 before the 5 does. The 5 is not supposed to receive that exponent, so we can't just make it a 10 there. What I do need to do before I start taking logs of anything is get that 5 out of the way. And so what I'm going to start with here is I'm going to divide by 5 first. And so now I have the equation 2 to the power of x equals 3 over 5, which is 0.6. And now from here, now this looks like all the other ones. So, and I think I can start to move through this a little more quickly. Exponent down in front, so we end up with x times log 2 equals log 0.6. And I'm going to do this divided by this to get x by itself. So log 0.6 divided by log 2. And we get negative 0.74. Okay, so 8, kind of a similar idea here. Before I start taking logs, that 22 is kind of in my way, right? I don't want to take a log until I'm down to just something that's exponential, until I'm down to just something to the power of something. So I'm going to move that 22 to begin with, make this a 37 over here. So now I have this, 3 to the power of 2x minus 1 equals 37. Now, I still look at this and see that I have an x up in the exponent, and that's still what's letting me know that I'm going to need to take a log on each side to get that exponent down into the base of the problem. So log here, move this entire 2x minus 1 down in front. So now I have this, 2x minus 1 times log 3 equals log 37. So I'm still going to divide by that log 3. All right, that's my next step. So I'm going to go log 37 divided by log 3. And I get this 3.29 number. But that's now, so that's this over here. And I've gotten rid of my log 3. But I still have 2x minus 1 left here on this side. So now I'm just going to solve this like a regular two-step equation. I'm going to add 1 to the other side, so I'm going to say this plus 1, okay? And so now I have 2x equals 4.29. And then I'm going to take that value and divide by 2. And I end up with x equals 2.14. Okay, these next two are really good questions. They kind of rely on these properties, but they rely on you being able to go the other way, being able to take something like this and separate it back into tiny individual logs. And I'll show you what I mean by that. So it says use the fact that log base b of 7 equals this and log base 2 or b of 2 equals this. And we want to evaluate log base b of 28. What I want to do is I want to think about what makes up that 28. Okay, what little pieces make that 28? And when I say little pieces, specifically, I want these pieces. I want 7s and 2s. So I'm going to start by rewriting log base b of 28. And I'm going to take that 28 out and replace it with 7s and 2s. So let's see, 28 is 7 times 4. So, and then 4 is 2 times 2. So I can write this as log base b of 7 times 2 times 2. So I took the 28 out and replaced it with 7 times 2 times 2. Choosing those numbers because those are the numbers I have to work with here. So using this multiplication property, if I'm taking the log of some things that are multiplied together, I can separate that into individual logs using addition. So when I see log of 7 times 2 times 2, I can separate that and say, oh, this is really log base b of 7 plus log base b of 2 plus another log base b of 2. So I took each one of these numbers and gave them their own log, all right? And then I combined those using addition. So now I know what this equals. I know log base b of 7 is this decimal up here. So I'm going to take this out and replace it with 1.7712. And I'm going to take this log base b of 2 and replace it with 0.6309. And I'm going to take this log base b of 2 and do the same thing. So this thing here that's written in green, that's what I'm actually calculating, all right, is I'm adding all of those decimals together. So I'm going to do 1.7712 plus 0.6309. I'm just going to say times 2 because I have 2 of them here, right? And you end up with this, 3.033. So I would say this is equal to 3.033. There's my answer. All right, we have to be careful on this next one with how we treat this exponent. And there's a few different ways we could do it. I'm gonna try to pick the way that I think makes the most sense. So when I see log base b of 1/3 to the 4th power, I know I need to rewrite this 1/3 using 12 and 4, and we'll get to that in just a minute. But I'm going to take this 4 down and put it in front of the logarithm using that exponent power. Changing my mind. I could do that. Mathematically, that's allowed, but I think that writing it that way might confuse people. So let me do this instead. Let me write this as, starting out, log base b of 1 to the 4th over 3 to the 4th. So I'm putting that power of 4 on the 1 and the 3. This is the part that people tend to miss, and that's why I'm starting by writing it that way. If I were to put that exponent in front, that's when people tend to make the mistake where they lose track of it on one or the other. So let me go with that. Okay, now let's think about this 1 over 3. 1 over 3 is really the same thing as 4 over 12. If I have to think about how I'm going to write this using exponents, 1 over 3 is the same as 4 over 12. So I could now say that log of 1/3 to the 4th power is really the same thing as log of 4 over 12 to the 4th power. And then I'm going to do what I did here. I'm going to put that 4 on each of those numbers. So I'm going to say this is 4 to the 4th and 12 to the 4th. So if that's confusing to you, just pause for a second and make sure you agree with me that this 4 to the 4th over 12 to the 4th is equivalent to 1/3 to the 4th. Okay? Once we're there, I'm seeing division here. So when I go to separate these things, I'm going to make them into subtraction. So I'm going to say this is log of 4 to the 4th power minus log of 12 to the 4th power. Be careful here because this says log of 4 to the 4th. It's not log of 4 being raised to the 4th power. The distinction there is I have some people who want to replace this with that decimal and then raise that decimal to the fourth power. That's not quite right. We can't replace with the decimal yet because we don't have log base b of 4 by itself. We have log of 4 to the fourth, but not log of 4. The way we're going to fix that is by taking this 4 and putting it down in front. So I'm going to take this 4 and move it down in front as well. So what I really have now, and I'm going to start back over here, is 4 times log base b of 4 minus 4 times log base b of 12. Now I can replace with my decimals. Now I can say that this is 0.7124, and notice that I'm multiplying by 4, and this is 1.277. Okay, so 4 times 0.7124 minus 4 times 1.277, and there's my final answer, negative 2.2584. That one is confusing because there's kind of 3 places that I see people making real common mistakes. The first one is just forgetting that this 4 really belongs as an exponent on the 1 and the 3. So I see them like multiplying one of the things by 4, but not the other. Okay, they'll put the 4 maybe at the beginning of this one, but not at the beginning of this one. By the way, you could also just do the subtraction and then multiply by 4 at the end. What actually, I think, is what would have happened had I moved that 4 down in the first place, but that's okay. So that would have worked as well. But that's one of the mistakes I see is people only applying the 4 to the one or the other. The big mistake I see is what I was talking about back here, is I see people wanting to say, oh, I'm just going to take this decimal and raise to the fourth power. That's what you would do if I were doing this, if I were doing log of 4 to the fourth power. But that's not what I'm doing. What I'm being asked to do is log of 4 to the fourth. And so this is different from this. And so we've got to be real careful about how we handle that exponent of 4. That really needs to be a multiplier, not an exponent when you get to that end stage. Okay, that's a lot of logarithms packed into one video. I'm going to carry on the next page. I'll start a second video so that this one doesn't get too terribly long, and we will continue working with logs and powers.